Hello, everyone. Hope all of you are fine. Today's topic is equipartition theorem, classical ideal gas, and Gibbs paradox. This is a very important topic and highly mathematical topic. So we are going to discuss all the three topics today: equipartition theorem, classical ideal gas, and Gibbs paradox. So let me come to the first slide. Yeah. So first is the derivation of thermodynamics. In the derivation of thermodynamics, a quasi-static thermodynamic transformation is considered. So in a quasi-static thermodynamic transformation, corresponding to a slow variation of E, energy, and V, volume, induced by coupling the system to external agent. So if we try to see that in a thermoflask, the thermodynamic transformation is taking place because of the connection with the external world. So for a small time interval, we can consider that the temperature remains constant. But for a larger interval of time, the temperature changes. And we know that in a thermal flask, for a small time interval, the temperature of the material kept inside remains constant. But if you consider a large time period, then the temperature does not remain same. So this is the quasi-static thermodynamic system. During such a transformation, the ensemble is represented by a collection of representative points uniquely distributed over a slowly changing region in gamma space. So the quasi-static state, the transformation is taking place in such a manner that for a small time interval, we can consider it is uniform in gamma space. The change is so slow that every instant we have a micro-canonical ensemble, and the change in entropy in infinitesimal transformation is given by equation number one. So at any instant of time, we can have a micro-canonical ensemble. So it is a constant at any instant of time. But for a larger time interval, it does not remain constant. So it is ds is an entropy function E and V by del S by del E at constant V dE plus del S by del V E for dV. And this is equation number one. And in this equation number one, the first term is defined as the term of coefficient dE is defined as the inverse of absolute temperature, that is T inverse. So the coefficient of first term is defined as the inverse temperature. And the pressure is defined as P equivalent to T del S by del V at constant energy E. So we can rewrite it P divided by T is equal to del S by del V at constant energy. So we can use this equation number three. We can use equation number two, which is defined as the inverse of absolute temperature. Using this in equation number one, we can write ds is equal to 1 upon T dE plus 1 upon T P dV. And we can take 1 upon T as a constant out of the bracket. So it is dE plus P dV. And in that case, taking a T on the other side, we can rewrite for the energy dE is equal to TdS minus PdV. And this is the first law of thermodynamics. Now we come to the another slide, general method to find the thermodynamic function. So we are going to see the general method. In some book, it is mentioned as a recipe, like a recipe of making any particular food item. So here we are going to use the general method for calculating the thermodynamic functions. So consider an isolated system that occupied volume V and has energy E within a small uncertainty or interval delta very, very less than E. Here, Hamiltonian is presumed to be known. To find all thermodynamic functions of the system, the following steps are used. So first, they calculate the density of states, which is represented by omega E of the system from Hamiltonian. So from Hamiltonian, we have to calculate the density of states, omega E. Find the entropy by using Boltzmann constant, K, by using a general formulations. It is a S function EV, K log omega E. And on the right-hand side in equation number 5 in a box, the several functions are given. So it can be calculated by S as K log gamma E, then S K log omega function E, S K log summation E. And we know that what are meant by that, that is again mentioned in the box in the bottom. It is volume in gamma space is represented as summation E. Density of states in gamma space is represented by omega E. And volume occupied in gamma space, it is again represented by gamma E. So these are the nomenclatures for equation number 5. So solve for energy E in terms of S and V. It gives the thermodynamic internal energy, that is U, is equal to E. So U is a function of S and V. Again, E is a function of S and V. And find the other thermodynamic functions using standard formulations. So once we find the internal energy U, then using these standard thermodynamic functions, we can calculate the other parameters, thermodynamic parameters, like a temperature using del U by del S, pressure del U by del V, and heat capacity CV del U by del T. So all the things are given in a box on the right-hand side by equation number 6. There are other functions like Helmholtz free energy and Gibbs potential. Helmholtz free energy is A equal to U minus Ts, and the Gibbs potential G is equal to U plus PV minus Ts. So those are represented by equation number 7. Now we come to the another important part that is known as equipartition theorem. So equipartition theorem is a mathematical one, and the base is lying in the classical mechanics. So let xi be either pi or qi. So it is a general representation. I is equal to 1, 2, 3 up to 3n. The ensemble average is required to be calculated. Now we use that dpdq is d3np, d3nq. So in a shorthand, we write dpdq. So ensemble average is represented as xi del x del h by del xj, and that is represented as equation number 8. So it is 1 upon gamma e integral. The limit is e less than h less than e plus delta, and dp dq xi del h by del xj, and that can be represented in terms of a delta divided by gamma e, delta by delta e, integral h is less than e, dp dq xi del x del h by del xj, and that is represented as equation number 8. And here the gamma is equal to summation e plus delta minus summation e, and that is represented by equation number 9. And we know very well that summation E is volume in gamma space enclosed by energy surface E. And that can be again represented, the summation E is represented as the volume occupied by energy surface E in gamma space. So it is H less than E, D3N P, D3N Q. And that is represented as dP and dQ. Now taking delta E by delta xj or del E by del xj equal to 0 and calculating the integral H. So some integral H less than E dP dQ xi del H by del xj, that can be represented as equal to integral H less than E dP dQ xi del by del xj H minus E, and that is equal to integral dp dq del by del xj, and in bracket xi in bracket h minus e, and minus delta ij. Delta ij represents del xi by del xj, and integral dp dq h minus e. So it is differentiated first for xi, and second is for the other parameter. So the first integral on right-hand side of equation number 11 is 0 because it reduces to surface integral over the boundary of the region defined by h less than e. So it is a boundary region and it is represented as 0. And on boundary region, we know that h minus e means h is equal to h and h is equal to e. And at boundary region, both are same and that is why it is becoming 0. So using the gamma E equal to omega E delta, where omega is called the density of states of the system at energy E, which is defined as the density of state omega E equal to del summation E by del E. And gamma E is again represented by omega E delta. These are represented by equation number 11. So now we concentrate on equation number 11. And as we have mentioned that it is differentiated in two parts. So delta by delta xj or del by del xj. First differentiating the h minus e and second differentiating the xi del xi by del xj. And that is represented by delta ij. And the first integral, as we have mentioned, that is becoming 0 because it shows the boundary condition or boundary region. At boundary region, h is equal to e because h minus e becomes 0. Now we come to next slide. Now using equation number 12 in equation number 11. Now ensemble average xi del h by del xj, that is represented as delta divided by gamma e delta by del e and integral h less than e dp dq xi del h by del xj. And that is equal to, by using equation number 12, the first term is 0. So it is minus delta x ij divided by omega e delta del by del e integral h less than e dp dq h minus e. Now we know that we interchange the term. So instead of writing h minus e, we write e minus h. So negative sign goes away. And in the numerator and denominator, capital delta is cancels out. So this cancels out. So this becomes simply delta ij omega e integral h less than e dp dq. That is represented as equation number 13. Now, if we assume that summation e is integral h less than e dp dq, as we have already mentioned earlier in equation number 10. So using equation number 10 in 13. So 13 we have already mentioned in the top of the slide. So it is ensemble average xi del h by del xj, and that is represented as delta ij divided by omega e summation e. Now that is again represented as delta summation e divided by del uh, summation e by del e. And that is again represented by delta ij in bracket del by del e summation e divided by del summation e inverse. And we know that delta ij in bracket del by del e is log summation e by inverse. So that is equation number 14. Now we know that the entropy can be defined in our earlier slides. We have already defined that S is equal to K log summation E. So it can be represented by S divided by K, and that is equal to log summation E, and that is represented by equation number 15. Now using equation number 15, we can write in equation number 14 that ensemble average, that is ensemble average xi del h by del xj is equal to delta ij in bracket del by del e s divided by k and on the bracket inverse sign. That is represented as delta ij k divided by del s by del k, del e. And again, we call it as equation number 16, which is represented by blue box. Now, using our fundamental definition, by definition, del S by del E is represented as 1 upon T. So inverse of a absolute temperature. So that is equation number 17. Using equation number 17 in 16, we can write the ensemble average xi del h by del xj equal to delta ij kt. And this is the generalized equipartition theorem, which is represented by equation number 18. And that is represented by green box. Now, for a spatial case, if you consider I equal to j and xi equal to pi, so it becomes a spatial case. So it becomes for momentum. So pi del h by del pi is equal to k. That is represented by equation number 19. For another spatial case, I equal to j, xi equal to qi. So it is qi del h by del qi equal to kt. That is represented by equation number 20. Now, according to the canonical equation of motion, del h by del qi is represented as minus p dot I, and that is the Hamilton's equation of motion. Now, we are using equation number 18. So in that equation number 18, we substitute the equation for Hamilton's equation of motion. So it is ensemble average. It is summation I 1 to 3n pi q pi qi p dot I. And that is equal to minus 3 nkt. So this is equation number 21. And this is known as a Widial theorem. So Widial theorem, we have already discussed in classical mechanics earlier, that can be represented as the ensemble average summation I 1 to 3n qi p dot I equal to minus 3 nkt. Now, in classical mechanics, the sum of ith coordinate times the ith component of generalized force is known as Widial, because p dot I is a generalized force. So the summation is the ith coordinate times the ith component of generalized coordinate is represented as y. And many physical systems, the Hamiltonian have the following form. So H is equal to summation of I, AI, PI square, plus summation I, BI, QI square. And that is represented as equation number 22. So here we have used the canonical transformation equation. So PI, capital PI represents the new momenta, capital QI represents the new coordinate. So where PI and Q are canonically conjugate and A and B are constants. For such a system, we can write the using equation number 19 and equation number 20, we can write summation over I pi del h by del pi plus qi del h by del qi. And we write that we are substituting for Hamiltonian. So just differentiating with respect to either pi or qi. So it is summation over I, pi to ai, pi plus qi to bi, qi. And ultimately, it becomes summation in bracket 2ai pi square plus 2bi qi square. And that is nothing but 2 times Hamiltonian that is represented by equation number 23. And here we have used equation number 22 and differentiating with respect to capital Pi and capital Qi. Now we come to the next slide. Suppose F is a degree of freedom and it is associated with the constant AI and BI are non-vanishing. Then using equation number 19 and equation number 20, we can write KTF is equal to 2H or the ensemble average 2H. And then we can simplify that H is equal to 1 half KTF. And that is represented by equation number 24. Now, it is a very interesting result. Each harmonic term in the Hamiltonian contributes 1 half kT to the average energy of the system. So each harmonic term is representing 1 half kT, equal amount to the average energy of the system. And this is known as a theorem of equipartition of energy. And this is also the internal energy of a system. So that is why it is known as an equipartition of energy. Each term, each harmonic term contributes 1/2 kT, average, equal amount of energy to the average energy of the system. And that is why it is known as a equipartition theorem. Now, using equation number 6 for heat capacity and putting equation number 24. So equation number 24 is the internal energy. So CV is equal to del U by del T. And it can be represented as del H by del T because internal energy and Hamiltonian are presumed to be equal. So just differentiating, thus differentiating, we can write, for the internal energy, and we can write in form of a internal energy, and we can write the equation in terms of equation number 25. So thus, the heat capacity is directly related to the number of degrees of freedom of the system. So as we have mentioned earlier, that using equation number 6 and putting equation number 24, we can simplify that del H by del T is equal to del by del T and 1/2 kT. And T is differentiated, it is equal to 1/2 Fk. And Cv, heat capacity, is represented as Cv divided by K equal to 1/2 F. So this is equation 20. And this equation number 25 is interesting one, very simple equation. So it mentions the building in a yellow box represented. Thus, the heat capacity is directly related to the numbers of degrees of freedom of the system. So F is the number of degree of freedom. And here the CV is the heat capacity, K is the Boltzmann constant, is a constant thing. So only the variation is between CV and F. So F changes, CV changes. So this generates a paradox. Now we write what is the paradox. And the paradox is shown in a black box. And again, the meaning of the paradox is shown in the box, pink box at the bottom. So the paradox arises from the theorem of equipartition of energy. In classical physics, every system must, in the last analysis, have an infinite numbers of degrees of freedom. One can resolve matter into atoms and its constituents to resolve the atoms into the constituent further into constituents, their constituents. So it is an ad infinitum. So we have a large number of collections of particles. They are having a constituents of molecules, their further constituents into atoms. Atoms can be divided into their constituents in terms of the electron, proton, and neutron, and further into the further constituents. So there are infinite number of particles, and they are possessing the infinite number of degrees of freedom. So therefore, the heat capacity of any system is infinite because infinite degrees of freedom can be assumed, and therefore F tending towards infinite, so CV tending towards infinite. So this is a real paradox in classical mechanics. However, the quantum mechanics possesses the feature that the degrees of freedom of a system are manifested only when there is a sufficient energy to excite them. So the solution is lying in the quantum mechanics. So this paradox is resolved in terms of quantum mechanics. We know that the heat capacity is a finite value, but here the paradox arises that as per this theorem, it should be tending towards infinity. So the solution of this paradox is given in terms of quantum mechanics. Now we come to the derivation of classical ideal gas. To illustrate the method of calculation in micro-canonical ensemble, we consider the classical ideal gas. The Hamiltonian is H is equal to 1 upon 2m summation over I to n pi square. And that is represented as equation 26. To calculate the volume in gamma space, the summation E, as we have noted earlier, so this is the volume in gamma space. It is 1 upon h raised to 3n integral h less than e d3p1 d3p2 up to d3pn, then d3q1 d3q2 up to d3qn. So this is equation number 27. And here we have introduced in the numerator the constant h. So the h is a constant of the dimension of momentum multiplied by distance to make the summation e dimension. So in this integral 27, it is integrated over pi and qi. So the dimension is momentum plus distance. So if we multiply by constant, which is having a dimension of momentum multiplied by distance, so the quantity summation E becomes dimensionless. So once it is dimensionless, we can do any mathematical manipulation, multiplication, division, whatever we do, we don't have to worry about the dimensionality. So to make it a dimensionless, it makes an advantage. So any further mathematical derivation, we don't have to worry about the dimension. So the integration over Qi can be carried out and giving the factor Vn. So we come to that R is equal to under root 2 me, and m is mass, E is the energy. So summation E is equal to V divided by h cube, and that shows the n number, and omega 3nr, and that is represented by equation number 28, where omega n is the volume of n sphere of radius r. There are n number of spheres of radius r. So it makes a volume omega n. So omega n r is again integration taken over x1, x2 up to xn square, which is less than r square. It is dx1, dx2 up to dxn. That is represented by equation 30. And that is shown in terms of omega nr, cn, rn, where cn is a constant of integration because these are the constants integration. So cn represents the constants of integration. Now, to find the constant of integration, Cn, we use the following identity. So identity shows it is equation number 32. So minus infinity to plus infinity dx1 multiplied by integrations. So final one is minus infinity to plus infinity dxn e to the power minus x1 square up to xn square, and that is represented as minus infinity to plus infinity dx e to the power minus x square raised to n, and that is a gamma function. So it is a very famous function in mathematical physics. So it is a pi raised to 1/2 raised to n, and that is pi raised to n by 2, and that is represented by equation number 32. So the left-hand side of equation number 32 can be represented as follows. So we focus on the left-hand side. So it is minus infinity to plus infinity, and that left-hand side can be represented as 0 to infinity dr as n r e raised to minus r square. Now, let us focus on equation number 33. Let S and R be the surface area of n sphere of radius r. So we have considered omega nr, that is the volume of n sphere. Now here we are considering the surface area. So S and R is equal to d omega nr by dr, and that is represented by equation 33. That is further represented as S and R equal to d omega n r by dr, and that is n c n r raised to n minus 1, and that is equation number 35. So if we put equation number 35 and 34, which is shown by arrow, that can be represented in form of equation 36. So 0 to infinity dr s n r e raised to minus r square equal to n c n 0 to infinity dr r raised to n minus 1 e raised to minus r square. That is equation number 30. So equation number 36 is represented over here. Now we play some mathematical trick and we assume that r is equal to t raised to minus 1/2, t raised to 1/2. So we write that dr is equal to 1/2 t raised to minus 1/2 dt. So that integral, equation number 36, can be represented as equal to 1/2 n c n 0 to infinity dt t raised to 1/2 n minus 1 e raised to minus t. And that is nothing but a famous gamma function. And gamma function is defined in a box on the right-hand side. So it is 1/2 n c n gamma n divided by 2 or n by 2. That is represented by equation number 37. Now, comparing equation number 32 and 37 and using the properties of a gamma function. So we can write Cn equal to pi raised to n by 2 divided by gamma n by 2 plus 1. That is equation 38. And for the coefficient, we can write log Cn tending to n by 2 log pi minus n by 2 log n by 2 plus n by 2. And if n tends to infinity, so by gamma functions definitions, we can write for Cn like that. That is represented by equation number 39. Now, using 28 and equation number 29, the volume occupied in gamma space is written as, so volume occupied by gamma space is, as represented earlier, summation E is equal to C3n V divided by H cube 2me, and that is 3 times, so 1 half, 1 half, 1 half, and whole bracket raised to n. So it is C3n V divided by H cube 2me 3 by 2 raised to n. That is equation number 4. Now, as per the recipe or as per the method we have already mentioned earlier, so we can write for the entropy of ideal gas can be represented by this equation. So the entropy of ideal gas can be represented as function EV k log summation E, and k is the Boltzmann constant. So we write it as equation number 41. So using 40 in equation number 41, we can write S equal to K log in bracket C3n V divided by H cube 2me raised to 3 by 2 whole raised to n. Now this can be represented by using equation number, that is for converting the logarithmic term. So S is a function of E and V equal to K. Now we divide the logarithmic term into the summations. So log 3n plus n log V divided by H cube plus 3 by 2n log 2me. So the term which was shown in a square bracket, now converted into the logarithmic form. Now writing equation number 39 for 3n instead of n as follows. So we in 39 we have written for the Cn, and now we have to write for the log 3 Cn C3n. So it can be written as the same equation for log C3n, and that is represented by equation number 43. Now using the value of log C3n of equation number 43 in equation number 42, one can write for the entropy function S function EV as follows. Now that is represented in a red box. So we focus on the red box. S function EV equal to K in bracket 3n by 2 log pi minus 3n by 2 log 3n by 2 plus 3n by 2 plus n log V divided by H cube plus n log 2me raised to 3 by 2. Now we concentrate that taking n common out of the bracket, so n is common, so it is kn again 3 by 2 log pi minus 3 by 2 log 3n by 2 plus simple 3 by 2 plus log b divided by H cube plus 2me raised to 3 by 2. Now the log term which is having 3 by 2 power uh, is taken common, and for h we have a h raised to 2 multiplied by 3 by 2 becomes h cube. So we write taking 3 by 2 common, so it becomes h square. So combining that in the third step, n k in bracket log 2 pi me divided by h square 2 divided by 3n raised to 3 by 2, because to make a power 3 by 2 we have done this manipulation for h, and in that case we have taken 3 by 2 common, so naturally it becomes h square. So by simplifying we can come to h cube like that, plus log v and bracket over plus 3 by 2 nk. Now combining the log term, so there is a small typographical mistake, so represented as nk, we have to put log there in bracket v in bracket 4 pi me divided by n 3n h square raised to 3 by 2 out of bracket 3 by 2 nk. Now, we are naming this as equation number 44. Now, we just do manipulation in that one. So, multiplying the term, uh, equation number 44 by 2 by 3. So, it is 2 by 3 function, S function EV. It is 2 by 3 NK. And again, there is a printing mistake. So, we have to put log there. And in bracket V, in bracket 4 pi ME divided by 3n h squared 4 raised to 3 by 2 bracket over plus NK, because we have multiplied by 2 by 3. Now, just we simplify it by taking nk or divided by nk. So it is 2 divided by 3 nk. S is equal to 2 by 3 log the whole square bracket plus 1, because we have divided by n. Now again, we are separating the terms, separating the log terms on the right hand side and simplifying the powers of the bracket. So it is 2 divided by 3 nk s minus 1, because we are taking 1 on the left hand side, log in bracket v 2 by 3, and again 4 pi me divided by 3n square n h square and raised to 3 by 2 multiplied by 2 by 3. So we are separating the terms, and in that case we can write it is 2 divided by 3 nk and function s function ev minus 1 log v raised to 2 by 3, and it is the power is nullified, 3 by 2 multiplied by 2 by 3, so there is no power. It is 4 pi me divided by 3n h square, and ultimately we are writing for the exponential term for the logarithmic. So it is e to the power 2 divided by 3 nk s minus 1 v raised to 2 by 3 bracket 4 pi me divided by 3 and h square. And now we are writing for E. So E is equal to, in bracket, 3h square divided by 4 pi m n divided by v raised to 2 by 3 E exponential. So E raised to 2 divided by 3 nks minus 1. And that is named as equation number 45. So equation number 45 is representing energy. Now, obtaining various parameters using standard formulation. So we consider that the energy we have derived is equivalent to internal energy U. So we have represented the same energy as internal energy U, and we call it by equation number 40. Now we know that by using the standard formulations, we can divide or we can derive other parameters as well. So for the temperature T, T is equal to del U by del S, and for the constant volume, so it is 2 by 3 U divided by NK. So just putting the value of U and differentiating. Now internal energy is equal to U, so U is equal to 3 by 2 NKT. So that is a very standard relation. And heat capacity CV is obtained. CV is equal to del U by del T at constant V. Now again, using the value of U, it is U divided by T, 3 by 2 Nk. So CV is equal to 3 by 2 Nk. That is represented by equation number 47. We can derive the value of pressure. So pressure P is equal to minus del U by del V. So it is 2 by 3 U divided by V, and that is represented as 2 by 3 in bracket, putting the value 3 by 2 NKT 1 upon V. So it is NKT divided by 1 upon V. So that is represented by equation number 48. Now, these are the thermodynamic relations we have obtained for ideal gas. Now we are coming back to the Gibbs paradox. We have already mentioned the paradox arised in equipartition theorem. So in equipartition energy theorem, the paradox arises. Now we think about the Gibbs paradox. Now this is a very interesting paradox. Gibbs gave a hypothetical experiment, and that gave the paradox. According to equation 44, after little modification, the entropy of ideal gas can be written as, so it is S is equal to Nk log in bracket V u raised to 3 by 2 plus n s0, where u is equal to 3 by 2 kt, s0 is equal to 3 by 2 k in bracket 1 plus log o pi m divided by 3h square. So these are represented by equation number 49 and equation number 50, which is given in yellow box. Now, considering two ideal gases having N1 and N2 particles kept in two separate volumes, V1 and V2. So in the diagram, we have shown that there are two boxes or containers of containing the particles N1 and N2 in volumes V1 and V2 at the same temperature, because the temperature is kept constant and allowed to mix in a volume V equal to V1 plus V2. The temperature is the same before and after mixing, and therefore the internal energy U remains unchanged. The change in the entropy is to be found out. So this is a mixing of two different gases. So the two different gases are mixed in a volume at fixed temperature. So the change in the entropy is to be obtained from equation number 49. So it is del X, which is a change in entropy, by K. So E is equal to N1 log V divided by V1 plus N2 log V divided by V2, which is greater than 0. Equation number 51. So this is the entropy of mixing. If two gases are of different type, then also this result is correct. So now we come to the what is the Gibbs paradox arised from mixing of the gases. Now the Gibbs paradox presents itself if the two mixing gases are of the same type. Since the derivation of equation number 51 does not depend on the identity of the gases, the same increase in the entropy is expected. In the hypothetical experiment, the contrast between mixing two quantities of ideal gases of different kinds and that of mixing quantities of the same type of gas. So there are two different type of things. One is the mixing of the same type of gas and of different type of gas. In the case of different gases, the mixing is accompanied by an entropy increase, delta X or delta S, which is equal to delta S equal to 2R log R. And that is representing the mixing of the two different type of gases. And in the case of the same gases, there is no change in delta S. So if you are mixing two different kind of gases, there is a change in the entropy. And if you are mixing the same type of gases, there is no change in entropy. So delta S is equal to 0. So this is the Gibbs paradox arised from the hypothetical experiment, which Gibbs assumed. Gibbs resolved the paradox in empirical way by postulating that we have made an error in calculating summation E. The number of states of the gas with the energy less than energy E. Gibbs assumed that the correct answer is n factorial times smaller than it was thought, by assuming that we subtract it from equation number 49. The term is log factorial n. So it is a Stirling formula. It is equivalent to n log n minus n. Now, it is represented by equation number 52 that shows the entropy of mixing. So S is equal to nk log V divided by n u raised to 3 by 2 plus 3 by 2 nk in bracket 5 by 3 plus log 4 pi m divided by 3h square. That is equation number 52. And that is a very interesting equation for mixing of two ideal gases, which was derived by famous scientist Tetrode and Sacker. So this formula does not affect the equation of state and other thermodynamic functions of a system, because the subtracted term is independent of T and V, because whatever we have subtracted, n factorial, is not dependent on T and V. For mixing of different gases, equation number 52 still predicts equation number 51, because N1 and N2 are the same constants before and after mixing. For the mixing of gases of the same kind, it gives no entropy of mixing, because the specific volume V divided by N is the same before and after mixing. The same type of gases we have assumed. If the gases are of different type, then V divided by capital N does not remain same, it changes. So equation number 52 is a very interesting equation. It was derived by two different scientists. So formulation equation 52 has been experimentally verified as the correct entropy of an ideal gas at high temperature. If H is numerically set equal to Planck constant, then it can be verified experimentally, and it is known as Sacher-Tetrode equation. It was developed by Hugo Martin Tetrode and Otto Sacher independently in 1912 for Boltzmann gas entropy. It is possible to understand classically why summation is divided by n factorial. It is not possible to explain classically. To obtain the correct state, the reason is given by quantum mechanics. So it is not possible to understand classical mechanically why we have subtracted by n factorial. But the answer is lying in quantum mechanics. Quantum mechanically, the atoms are inherently indistinguishable in sense that a state of gas is described by an n capital N particle wave function. So there are n particles, so n particle wave function describe the state, which is either symmetric or anti-symmetric with respect to the interchange of the two particles. So which gives either symmetric or anti-symmetric nature. So a permutation of the particles can at most change the wave function by a sign, does not produce a new state of a system. The gamma space volume element dpdq corresponds not to 1, but only to dpdq divided by n factorial state. Therefore, summation E is divided by n factorial. And this rule of counting is known as a correct Boltzmann count. Now we try to understand this particular nature by our famous game of cricket. We know that in cricket, there are two types of batsmen. One is a right-handed, another is a left-handed. So we have to make a different fielding arrangement for a right-handed batsman or left-handed batsman. So if running between the wickets of two different batsmen are taking place, if both are right-handed, then running between the wickets of two batsmen will not invite the change in fielding. But if one batsman is right-handed, another batsman is left-handed, and if running between the wicket is taking place, then we have to change the fielding arrangement whenever the bowling is faced by a right-handed batsman or bowling is faced by a left-handed batsman. If both batsmen are left-handed, again running between the wickets does not invite change in fielding. But the change in fielding requires only when one is left-handed, another is right-handed. So the permutation and combination we have to decide depending upon the type of the nature of the batsman, whether both are left-handed, both are right-handed. If one is left-handed, one is right-handed, then change in the fielding is taking place. So like that, we can try to understand the symmetric and anti-symmetric nature of the wave function. So it is represented over here by a picture from the game of cricket. Now, for further reading, we suggest that the statistical mechanics by Huang. And now we come to the contributors' contribution. One is a contribution given by the John James Waterston, born in 1811, died 1883. The Scottish scientist worked in India as a civil engineer in Mumbai. And in 1845, he proposed equipartition theorem and he presented it, but it was not accepted at that time. So the engineer worked in India and proposed equipartition theorem from India. Another scientist, James Clerk Maxwell, born in 1831, died 1879, Scottish physicist and mathematician, and gave final form of equipartition theorem in 1859. The ideal gases are again given by the French chemist, so Emile Clapeyron, 1799 to 1864, French physicist and engineer, known for his contribution for ideal gas theory. And Joshua Willard Gibbs, American physicist and physical chemist, born in 1839, died in 1903. He gave the Gibbs paradox. And the picture of Hugo Tetrode, Dutch physicist, born in 1895, died in 1931. And the German chemist Otto Sucker, German physical chemist, born 1880 and died in 1914. So they contributed in particularly the different field of the statistical mechanics, mixing of ideal gases, deriving the equations and thermodynamics for ideal gases. So here we recognize their contribution. The last one is a very interesting slide. These are the two pictures of the one is the Niagara Fall in USA, another the small mountain fall. These are the signifying the energy of water particles. And thank you very much for patient hearing. Now I will stop sharing the slides. Thank you very much. Thank you very much. Thank you very much. Thank you very much. Bye-bye.